Welcome back, quantitative analysis students. This is Mr. Marquetta, and tonight we're going to explore linear inequalities and linear programming. This is associated with chapter 4.1 and 4.2, which for summer session 2022B is in your subfolder 5A. All right, here we go. First, let's talk about what Desmos looks like when it comes to graphing inequalities. And also let's try to remember what it looks like to graph an inequality. You may recall when you were in the 9th grade or maybe the 11th grade, you may have been introduced to graphing straight lines on graph paper and maybe also inequalities which require shading. Maybe you remember coming up with a model equation. For this one, it would be just the inequality you're looking at there, but having an equal sign. And then you would graph that 3x minus 2y equals 4. You graph the line. And then you would make a test point. You'd say, well, let's see, which side do I shade? Do I shade to the top left of this line, or do I shade to the bottom right of this line? And then your process with arithmetic with a pencil is choose a point, an arbitrary point on either side, and test to see if it's true in the inequality. For example, if you use the origin, which you could see is right here. Let me go and grab that. Here's the origin right in the middle, right? Oops. There we go. And if you say, well, the origin happens to be a great point that we could use because it's clearly on the opposite side of the line. So we put 0, 0 into this inequality and we get a statement that's obvious just to the naked eye. 0 is greater than or equal to 4. That's false, right? Because the origin is a point 0, 0. So if I put 0, 0 into the position of x and y right here, can you see that the left side of my inequality becomes 0 then, of course, right? So 0 is greater than or equal to 4. That's a false statement. That means that the origin and any surrounding points are not part of the solution set. Instead, if we tested the other side, we would get something that was true. For example, maybe 5, 0 right there. A point like this, 5, 0. If you put 5 and 0 into the positions of x and y, you'll get the statement 15 is greater than or equal to 4, and that is true, so you shade. Now, you probably remember doing that, just reviewing it briefly, because you don't need to do that here in our class. Remember, we're learning about how to use technology to aid us in getting these answers. And so with linear programming and linear inequalities, we don't really need to do that test point thing. We don't really need to understand how to graph a straight line. We don't really need to understand that as much as we need to know how to read it in Desmos. What you're looking at is an actual graph in Desmos after you type in that very basic simple inequality. You can get that symbol greater than or equal to by pressing the little keyboard on the bottom. If you have a graphing calculator, there's also ways for you to come up with a graph in the same way. What I want you to be comfortable doing is coming up with graphs that you can apply and use. So for example, take a close look at the axes here. You'll notice in the picture that we're looking at, the x-axis goes from -10 to 10, and then the y-axis goes from -10 to 10. So this has a window of -10 to 10 for both x and y. When you do your homework in WebAssign and you have questions that say, which of these graphs represents the inequality, you'll have multiple choices of many different pictures of graphs. Remember to look closely at your multiple choices to ask, what kind of span do I have of a window? And use that window when you go into Desmos and look at the function, or at the, in this case, inequality or the program. So remember that, how that works with the wrench. Okay, and we're going to use that a lot today because we want to make sure that we get a good, appropriate pictures of the inequalities. One other thing I want to try to get you to remember from those days when you were studying inequalities, you might recall that sometimes it was a solid line and sometimes it was a dotted line. Take a look at our picture here now. Notice that there's a blue solid line there. Here's another example of a great inequality that we could graph as well. Notice this inequality does not have an equals in it. It's just greater than, whereas the other one is greater than or equal to, right? So look at how it doesn't have a solid line. It has a dotted line. So I just remember that those little details make some of the questions easier, because if you understand that less than equal to or greater than equal to has a solid line because of the equal piece. Whereas if it's greater than only, or if it's less than only, you can expect a dotted line like you see there. Something else I want to make sure is very clear about inequalities before we go forward. The fact that it's greater than does not necessarily imply that you're shading above the line. And some students make that mistake too, thinking that when I see greater than, I don't need to do a test point. Greater than means above, I just shade above. An example, the green one, if you look for the green one with the dotted line, in that case is greater than, and yeah, it's shaded above. Take a look though for a minute, friends, at the blue one. The blue one says greater than, and look, it's kind of shaded really below. So I want to just break that idea in your mind if you have it, that greater than means shade above. It does not. What it means is use a test point, or even better, use a graphing utility like Desmos to see where the shading really is. You cannot assume that if it's greater than it's shaded above, or vice versa in any way. Okay, so that's your introductory of what it looks like to graph simple inequalities. Now, thinking about what would it be like if you graph two at the same time, which is the picture you're looking at here. If you think about it in the same way you consider a system of equations, instead of it being a point where two lines cross, consider it like it's a region or area where two other regions overlap. That's what you're thinking about when you say linear programming, okay? Because linear inequalities are one subject, but then like the application of that is the concept of linear programming, which is when you can make up inequalities based on a situation and then see how they overlap. So that's what our lesson is about tonight, really, linear programming. The intro to it is being comfortable with linear inequalities, as you see here. And I want you to consider the idea of what it's like for them to overlap. If I asked you to graph the system that is these two inequalities, the program, which they call it a program instead of a system, the program, it would be the intersecting piece only. In other words, I'm going to try to highlight something to show you what I'm talking about. In other words, I'm using a funny spray paint can here. Okay, so just bear with me. This piece right here is all gone, and this piece is all gone. Okay, and what you got only is this piece here, and then the dotted lines here, you know, and then all the shading inside of there. That's the answer, not the red, just the black that I showed. So when we talk about a program of inequalities, the same way it's like a system of equations, it's the same concept. The answer is the overlapping region only, and you have to kind of look at both inequalities and like use an imaginary pair of scissors and cut out the green piece above and cut out the blue triangle below. You know. And by the way, I want to mention also at this point in our conversation that your solution region is not necessarily a bound polygon. It might be having edges like this, but then if you think about this piece, it goes on forever to the right in an area that expands forever. So you have to consider that the answer is not always a nice, neat triangle something. You know, you can never see all of the answer because of, you know, when you look at the plane, you only can see a piece of any plane anyway. They're all infinite. So think of it also that it's kind of a partial polygon is what your answer looks like. Okay, I hope that helps a little bit. That's the real truth about the story of the linear programming is you have to have a good grasp on linear inequalities and connect it to what a system would be. Okay, so that's the actual algebra of it. Let's go through the motions of seeing what it's like to use Desmos for the first time to just graph an inequality. Here, I'm going to ask you to try to go ahead and graph this inequality. It's 4x minus 2y is less than or equal to 6.
Hey, Professor, sorry.
Yes.
I direct message you. Isabella went to class, so she told me to tell you that she'll be online in a little bit because she went on.
I appreciate you sharing that. Thank you. I'm sorry to interrupt you, but thank you so much for letting me know. I'm sure we'll see Isabella real soon then.
Cool. Thank you.
Thank you for telling us. Appreciate it. So let's see what it's like to graph. This is 4x minus 2y less than or equal to 6. I just go right in and type in 4x minus 2y like so. And then to get my less than or equal to symbol, I'm going to come down here to this little keyboard symbol down here on the left, and I'm going to open it up, and then I'm going to look for that less than or equal to. Here it is. And then I'll go back in there. I could close my keyboard now like so, and I could go in there and do a 6 like that. And now you could see I have a picture. And if Desmos wanted the picture to look a certain way, like from here to there or something like that, I could change it around if necessary. Okay. It's funny looking. I do expect it to be shaded on one side or the other. Notice that we chose the color pink here, or salmon, or whatever you want to call it. In the other image that we were looking at, it came up as purple, right? But that doesn't matter. What matters is that you see shading, and Desmos is always creative with the colors that are being used there. All right, so graphing an inequality, type it in. Remember, if you need an inequality symbol, you can always just go straight over to that little keyboard over there, click it, a little menu will pop up, and then all the symbols are there that you could need, and it will graph them. But it'll also graph more advanced things that are nonlinear, and you can make really interesting, beautiful shaded regions and stuff, playing with parabolas and stuff if you want with it. So experiment with it. It's a really great thing to experiment. Let's take a look at the next slide. We're going to talk about a graphical solution. So please graph the system. What that means is graph the two of them, and then where do they overlap, and then write that as your final answer where they overlap. So here's what we would do. We would go in and put the two of them in there, like we showed earlier, and then we would see where they cross. It's the same thing I just did, so I don't think I need to go to Desmos and actually type them in. You see the point. Basically, you go and you type them in, and here's where they cross. As a reminder, friends, don't forget that you want to make sure that you include only the intersecting piece, including whether it's got dotted lines or not, and then everything inside of there too, like that. We're not going to include this piece here. We're not going to include this piece here. Only that little funny triangle on the side there. All right. Okay, now let's talk about a special kind of program or system where you can say, let's just stick around to positive numbers because I'm talking about prices and quantities or whatever situation, usually in more practical math where you're doing applications of real world situations, you don't have to consider negative values. So the easiest way to come up with a system that includes the limitation of only positive numbers, please, is to include this interesting syntax right here. I'm going to show you. Right here, you see there are two inequalities, and then underneath it all, it says right here, and by the way, x and y are both positive or equal to 0. It cannot be negative. The way that you do that is after you include your inequality, you just type this syntax directly after it. And what happens is we have a natural bound of the y-axis and x-axis such that you're looking at only a right angle kind of image, something like the purple and blue triangles that you see on the left there. Very popular for doing supply and demand curves and market equilibrium and things like that, because it's not just two lines that intersect, but it also represents all of the area underneath, and different applications can be used in that situation. So if you're looking at situations where you have a third condition, besides the first two inequalities, there's a third condition with that interesting syntax. Don't read too deeply into it. Just think of it as that means no negatives. That's what that means. And if you type it in a certain way, you can include that on any inequality that you use. If you only include one of them, you can, like, in other words, if you only type in fancy bracket x is greater than 0 fancy bracket, just the x one, then what'll happen is it'll let it go past the y negative, but it won't go below the x negative. So you can do that, and you can do that not just with 0, you can do that with any number you want to if you need to. But the point of it is it's just a little bonus added to the idea of a program of inequalities that you could add. So here's a good example of a system that has a situation where we have only positives and zeros. The way you handle it is type in the system of equations the way that you would have in the first place, but just also include, when you're done with each inequality, that interesting syntax that I have highlighted in the box, and then you'll get a picture like you see on the left where we have bounds using the x and y axis. So now the other thing is, if you see it there, you can imagine in your mind knowing that it stops there, and then when you go and look at the multiple choice in WebAssign, you can choose the one that obviously stops there. Maybe you could see it and you don't need to type it in, and that's okay too. Because remember, it's just Desmos. It's a tool for you to connect with WebAssign, putting the right answers in and getting the application ideas right. All right. So why are we doing this? Why are we learning about how to put all of these inequalities on this graph paper and shade in the right place? What does it all mean? Well, there is a practical application about it. This is the situation. We're going to do two situations tonight. For the first situation we're going to talk about tonight is a manufacturing plant that makes coffee makers and cappuccino machines. Another thing we're going to do tonight is talk about a farm that makes corn and I think it's soybeans. I can't remember. It's corn and another vegetable. And there's limitations. The limitations on the farm are you only have so many acres and you only have so many people that are laborers that can work the farm. Here, some of the limitations are you only have one plant in Atlanta that can make only so many, and one plant in Fort Worth that can make so many of each of these different situations, of each of these different items. Here, it's a coffee maker. So let's read the example, and then I'll show you what I mean. All right, we're going to read this and try to write a program of inequalities that describes a situation and then solve the program of inequalities. CDF Appliances has assembly plants in Atlanta and Fort Worth, where the company produces a variety of kitchen appliances, including a 12-cup coffee maker and a cappuccino machine. The following table shows each factory's assembly capabilities for the two products and the numbers needed to fill the orders. So at a little glance and summary of this table, I'm noticing that we can make 160 coffee makers per hour in the Atlanta factory, and we can make 800 per hour in the Fort Worth factory. That tells me Fort Worth is the better place to make coffee makers, maybe, I don't know. Also, I see the cappuccino machine. You can make 200 of them in Atlanta in an hour, and you can make 200 of them in Fort Worth in an hour, which tells you both of them have about the same capability with the cappuccino machine. The coffee maker and the cappuccino machine represent the product or the actual thing, the crop, the thing that you're selling, your item, the kinds of items you have are over there. And then the conditions about how those items can be created, you can see if you look across the top of the table. Atlanta and Fort Worth have conditions because of the size of their plant and because of the employees and the story of what the Fort Worth one looks like versus what the Atlanta one looks like. So thinking about that, we have a table here, and we also have a certain specific requirement. Like imagine that there's a day coming in your future, it's on your calendar, where you're about to sell a large amount of your product to, say, Starbucks or whatever, Wawa, or whatever you're doing coffee to, right? That day is coming, and when that day comes, you need to have 64,000 coffee makers, and you need to have 40,000 cappuccino machines. That's what you promised in your contract or something like that. The needed part on the end are the requirements. And based on this whole situation, we have statements that are called constraints. There are certain things that must happen here if I'm going to achieve my goal. And it's associated with the numbers you see in this table. Look at what it's asking you to do. Write the system of inequalities that describes the number of assembly hours needed at each plant to fill the orders and graph the solution needed from the system. This can feel a little bit confusing because there are hours and there are also actual machines. Coffee makers and cappuccinos, that's a different count than hours. And it's a little tricky to see how they go together, but you have to think about them as describing an entire row. Take a look at this row first with me right here. As for coffee makers, I need at least 64,000. So if I need at least 64,000, when it comes to coffee makers, I can make 160 of them in X hours at the one place. I can make 800 of them in Y hours at the other place. X is the number of hours at the one place and Y is the number of hours at the other place, right? And then when it comes to the cappuccino machine, I have a similar statement. I'll use green for that. For the cappuccino machine, which is this piece here, we have a new statement that is associating the concept of having 200 machines times the number of hours I can work the Atlanta factory, right? And the same thing with 200 machines times the number of hours I can work the Fort Worth factory. That ought to be greater than or equal to what I need, which is I need at least 40 grand. And now, by the way, you can't have negative coffee makers and you can't have negative hours, right? And such. So we include our little extra syntax to show that we mean nothing negative. When you graph those three things, you get something looking very much like this right here. I'm going to pause there for a minute because this is pretty deep stuff. I want to make sure that you have a good grasp of what we're talking about. I'm going to repeat the idea. Okay. In this one, example 4, they're only asking you to write the system of inequalities and to graph them. There is another step we could do that we're going to talk about that actually makes this linear programming. This is not exactly linear programming yet, but this is kind of the last thing you need to know before you're able to do linear programming. As you can see, it is once again an application of inequalities. Graphing the inequalities is not a very difficult situation, especially considering you know how Desmos works and that you can zoom in and out of Desmos to get them. I think we should do that with this one so that you can see what I mean. Because notice that we need to know for 200 and for 400. Like I'm looking right here, guys, at this. Right here, you'll notice I have this is going up to 400. And then right here, you'll notice I have this is going up to 500. That's going to make a significant difference of what the polygon looks like when you put them together. And not to mention, we're not talking about -10 to 10. We have values in the hundreds here. So we're going to have to change our view in Desmos to be able to really get a good look at that. Let's go through that and see what that feels like. I'm going to get rid of these drawings. And I'm going to take these inequalities that I have, all of these right here. I'm going to carefully type them all into Desmos in the way that I showed you. And then we'll get a nice picture that hopefully looks very much like this graph. That's an important skill set that you have to have mastered to be able to do your practice homework. Let's do one of those now. So we'll move over to Desmos now. And I'm going to take a minute and type them in. I encourage you to do the same while I'm doing that. And then I'll move over to Desmos. And that way you can see them. Right now I'm typing them into Desmos. (160x) plus 800y is greater than or equal to 64,000. And 200x plus 200y is greater than or equal to 40,000. Okay, friends, let's take a look at Desmos now. So I have the two systems in there. I don't see them anywhere. Of course, that's because, like we said, they're in 64,000 way up there. We're looking at from -10 to 10 and -6 to 6. Also, we want to include the fact that these inequalities are in the first quadrant only, and that they do not have negative quantities. So we're going to include that interesting syntax. Let's put that in. Here I'll write, right after this inequality, right after it, the fancy bracket. By the way, let's talk about that. I know that sounds silly, but that is the technical syntax word, punctuation vocabulary word for what you're looking at. That's called a fancy bracket. It's not a square bracket and it's not a parenthesis. You have to use the fancy bracket. It's next to the P if you hold shift. And in the fancy bracket, you tell us x is less than or equal to 0. Oh, greater than or equal to 0. Sorry. Close the fancy bracket, open a new fancy bracket, y is greater than or equal to 0, and then close the fancy bracket like so.
For some reason, I'm getting like the triangle with the exclamation point, that there's like an error in Desmos when I put the formulas in.
Let's take a look. Let me see if I can get this up first. Hold on just a minute. Let me take this and copy it. You could even copy it. Let's see. Is it this thing you're talking about? This exclamation mark, right? Okay. Are you let me see. Let's zoom out and see if we can get an image, and there's the image. Okay. Now, if you're getting it, take a close look at your writing. You might have included a comma. Don't put commas for 40,000. You might have put.
Oh yeah, I had commas.
That's I nailed it. You're welcome. Just don't put commas in, and it will work just fine. If you zoom out a little bit, does it look like my picture now?
Yeah.
Okay, good.
Yeah.
All right, so you're welcome. So now we're asking to show an actual graph of this, and when we do that, notice we couldn't see it earlier, but now I can see that it does kind of stop at the X and Y axis, particularly kind of like right here, you know, and right here. See, it won't go down below there and come out of that region because it's stuck in there. It's hard to see because it's kind of an inverse or upside down one or a backwards one. Anyway, now that we have that there, let's see if we can match the actual image that we saw in our textbook. In the image we saw in our textbook, we were going only from 0 to 400 and then from 0 to 500. So what I would do for that is I would go over here on the right and I would click on the wrench like so. Okay, and then I would tell Desmos, please show me the x-axis from 0 and maybe not 0. Let's go like negative 100, so I have a little bit of something over there, you know. And then we'll go to say maybe 600 or 500. But if we go to 600, we get a little bit past it. I like to go a little beyond the picture, so you kind of have a little bit of a boundary. For the y, let's go from negative 100 to 400. And now, if you look at our picture, it's really very, very close to the actual picture that we were looking at before. In fact, these lines right here even kind of look like they're the correct slope, this one and this one connected to what the picture should look like. Steve, I'm trying to draw it on the line. I think you know what I'm saying. But that's what we have as our answer, and we've come up with a great program here. Thing is, you just want to make sure that you're kind of connecting it to whatever those multiple choices are in WebAssign. Okay, great. So let's come back now. And you'll notice that they've included here the equations of the lines. You don't have to write that. They just did that to give you further explanation. But something that is kind of important that I want to focus on for just a minute. Look at how they've purposefully highlighted all of the points. This point right here has been highlighted. This point right here has been highlighted. And this point right here has been highlighted. These are called the corner points, of course. What else would you call them, right? But these are called the corner points. And it's something important that we have to talk about now that we've gotten to this level. We've learned about how you're supposed to graph an inequality. We've learned about how you're supposed to graph two inequalities. We've even gone so far as keeping them in the first quadrant. But why? Well, the corner points are the most important extreme places in the polygon. And we need those points, and we need to look at them closely and see if they help us when it comes to maximizing a value or minimizing a value. So what is linear programming? Ultimately, it's a method where you come up with a graph like you see here, and then you observe those corner points and use the values in those corner points to come up with a final conclusion. That final conclusion is found using something called an objective function. Okay. So here's the basics of linear programming. They give you an objective function. It's in the format f of x comma y. What that means, and I'm going to highlight that right here, what that means, f of x comma y, that means that if I tell you that x is 2 and y is 7, for example, like how those corner points have an x and a y, well, there's a function, f of x, y is like a polynomial that has x and y in it. You just put them in positions where they go. It's like substitution. And then you get a number, right? So you graph all the constraints, which we just did many times. You observe all those corner points, which I just showed you for the first time. You could go and find those corner points. Then you find f of x, y for each point. That means you take the values in each point and plug them into the objective function, which will be defined up front, and it'll be a polynomial in x and y. Then select the f value that is the max or the min, and then depending on the image, it should be clear sometimes when there's no max or when there's no min. Hard to explain without showing an example. Let's look at an example. It'll make a little bit more sense what I'm trying to say. So here we have a case where we're just doing algebra here. We're just doing math. We're not doing an application. We're going to do this to a farm with corn and soybeans in a minute. But this is the actual math of it. Okay, the actual math of it is maximize the objective function. And you'll notice it says f equals 3x plus y. Imagine the corner points of your program and whatever x and y are, putting them into that formula to get a value for f, and then doing it again and again for each of the different points to find out which point gives you the biggest f. This is to maximize f. You might be asked later on to minimize f, okay, where you take the values of the corner points and plug them in there. How do I get the corner points? I go to town with this program right here, and I put them all in a Desmos and see where the corners are. So we've already talked about how you do that. I don't want to waste your time and do that again. But I do want to get to the point where we get objective points or corner points to do objectives. So we will graph this function. In Desmos, it's a piece of cake to do. And after you graph it, you can click on the corner points and it will tell you just what the corner points are. Case in point. Let's go back to Desmos for just a minute. When I was looking at this, what were the corner points? Well, remember, in this situation, the actual polygon is only right here. Right? So that means I have three real important points here. Those points are this one here, this one here, and this one here. Notice that the other things like the blue line and the green line, I'm not considering. How many points are there here? There are three. Notice that there is no max to this function. Does it not go up forever and ever? The green ink, it goes forever up. So there are only mins to this function. There are no maxes. Sometimes it's the other way around. And sometimes, you can only interpret that looking at a graph of a program like you see here. So now with this beautiful polygon, I can take all that writing off there. And I could say, what are these important points? Well, I just got to kind of click on them and they come right up, Isn't that funny? I tell you, you click on it and it comes right up, and it's not coming up. Yep, it's not coming up. Take these off for a minute, maybe it'll come up. Let's see. There they are. So if you take those off for just a minute, it'll come up. I don't know why, but you have to take them off. So also I can find out that's 0, 200. See that? This one here is 150, 50. And then this one over here is, so what I would do is I got X and Y for each of these, Here I would take X is 0 and Y is 200 and put it in F and see what I get. Then I would do X is 150, Y is 50 and put that into capital F and see what I get, and do it again with these numbers into F and see what I get. And then which of those is the lowest number? One of them will be the answer, and only one. There's no rhyme or reason to which one it is. It's not like it's this one here because it's the lowest one. You can't, there's no rhyme or reason to it. You have to test all of them and see which one gives you the lowest. And also one of them will give you the highest as well. But in this case, the one that gives you the highest still isn't the best because this one is for infinity upwards anyway. So let's do an example now that you got that idea. What we would do then is we would graph these three, right? And after we graph these three, we get the points like I just showed you. And here are the points. Let me just highlight them. Here are our points. We have 0, 10. We have 10, 8. And we have 14, 0. Those are our points. So here they are. And we carefully put them all into the function f. And notice that out of all three of these, one of them wins the prize. It's this one here, of course. It's the largest. So the maximum value is 42, and it happens at x equals 14 and y equals 0. That is linear programming, is taking a system of inequalities that represents overlapping regions, consider its solution, which is the polygon or half polygon that I explained, or odd polygon or unfinished. Then there are corners. Then you use the corners and put them in the F. Look back at the question, say whether they want maximize or minimize. This time they want maximize. So I'm looking for the largest number. The largest number was 42. And the answer for 42 is the 0.14, 0. That's the solution to the linear program. So we have one more example to go through, of course, because now I have to show you how to apply this. Okay, because this is the idea and it's an algebraic, beautiful thing. Isn't this just a lovely little what would you call it? Busy work for the kids in Algebra 2, right? No, there is an actual application here because you could talk about a plant that has, say, coffee makers and cappuccino, and you want to maximize the profit or minimize the cost. And what happens is these corner points start to give you an answer that you could either spend $42,000 or $38,000 or $10,000. I think you should spend $10,000, and this is what we mean by programming, is using these constraints to come up with statements that are true, that we believe, and that we can apply in this way to get answers. Let's do one more where we actually do an application. This is the one I threatened earlier to do about the farm. Here it comes. And it was soybeans. Okay, I was right. I couldn't remember if the second one was soybeans or what. Anyway, Farm Co-op has 6,000 acres available on which to plant corn and soybeans. The following table summarizes each crop's requirements for fertilizer or herbicide, harvesting labor hours, and the available amounts of these resources. And not unlike the coffee machine and cappuccino maker table, where we had two cities, Fort Worth and Atlanta, here we have instead not items we're producing, but supplies that we need to be able to create our crop. We need fertilizer and we need labor. How much do we need? Well, for when we're growing corn, we need 9 gallons of fertilizer per acre. And we also need 3/4 of an hour of work per acre. Don't let the 3/4 throw you off. Just imagine it's a quantity. You'll use it later and Desmos will deal with it anyway. But in other words, a certain amount of time connected to each acre of labor that you have to pay employees. So it's another expense, just like buying fertilizer is an expense. Okay. Then the same thing with soybeans. And when it comes to soybeans, you know, in the case of soybeans, you also have, you need 3 gallons of fertilizer per acre. Notice corn takes more. I always mention little ideas in my head like that when you're looking at a table. And likewise, we need an hour of work harvesting for soybeans per acre. So it looks like it might take less ingredients like fertilizer, but it takes more labor, right? So we have kind of a funny crisscross going on here. And by the way, when it comes to how much fertilizer we have a constraint. We only have 40,500 gallons of fertilizer. That's it in our barn. We only have that much. So instead of it being that it has to be at least something, it's at most something. I cannot spend more than 40,500 gallons of fertilizer. That's my maximum. I have no more than that. It's the same thing with how much labor do I have? Well, I only have so many employees, and these employees each do 40 hours a week, and the total number of hours I can possibly do on my farm only is no more than 5,250. So see how it's a constraint, how it's something that is a limiting thing, and those limits kind of dictate what you can do, and you can do it in many different ways, hence many different corners on the polygon. The objective is to figure out what is the best way to do it to get you the best profit, or to cost you the least. In this case, we're going to try to make it the least, you know, or the most, because it's about profit. So look at the first question now. It says, if the co-op's profits per acre are $240 per corn and $160 for soybeans, then how many acres of each crop should the co-op plant to maximize profit? I misread that. And what is the maximum profit? So can we come up with a profit function? Yes, we can. We are told some specific things about the profit. Here are the little hints about the profit. Your profit is 240 for corn and 160 for soybeans. Maybe we should let X be the corn and Y be the soybeans. And we could say that the profit would be represented by 240x plus 160y. Likewise, we are told up here that we only have 6,000 acres, right? So isn't it true that all of the corn plus all of the soybeans can't be bigger than 6,000? That's only a farm is only finite. There's only so much in the farm. How much is in there? 6,000 acres. Well, if X is the number of acres of corn and Y is the number of acres of soybeans, well, I guess X plus Y better be less than or equal to 6,000, because I only have that much property. These are all the different things you have to consider as a business leader when you're thinking about profits, and it comes along with it coincides with the concept of linear programming. So we do have an objective function coming out from the purple rectangles where they're telling us what the actual profit can be made up as. We also have constraints in terms of land here, how many acres we have. We also have constraints in terms of herbicide and fertilizer. And then last but not least, we have, of course, labor constraints. And you can use those words in your speech, and it sounds very important, you know. But basically, the word constraint is like a limitation. It's something that, since this is all that we have, so this is the best we can do. So let's take a look now. If we're going to maximize the profit function is going to be given according to the concept of how $240 per acre can be made of corn and $160 per acre can be made for soybeans. So that's why P equals that. Next, here are the constraints. First, we have a land constraint. We told you right in the beginning that the farm only has 6,000 acres. So the acres of corn plus the acres of soybeans must be less than or equal to 6,000. That's what I'm looking at right here, friends, right? Because I'm still here now. I hope you're following with me. This is where we are, right? We just did these two. Now there are other things. These two, and I'll highlight them together. These two came right out of the table using these numbers. And by the way, we can't have negative acres of corn. We cannot have negative acres of soybeans. So we're going to say we're only going to remain in quadrant 1, and we're going to never have negative values, which is what the syntax means. And when you do it, it's kind of hard to see it here, but there are actually many points. There are 5 points. And the reason why there are 5 points is because you don't just have 2 constraints, you have 3. Look, you have 1, 2, 3 constraints. If you look, I have 3 lines, and let's look at them each. The first one is this one here. The second one about the fertilizer is which one? Is this one here. And then the labor one is here. Notice that it makes 3 distinct dots. I'm going to highlight them. Here's one of them. Here's one of them that you can't see, and here's another one that you can't see. In other words, there are 3. And if you consider that there are also, of course, in the polygon these, there's this one and this one as well. It really means that there are 5 points. For extra measure, if you want, you could go ahead and test 0, 0, but 0, 0 is going to give you 0. But I mean, you could. But theoretically, there are really 6 points. You should check all of them. We know already that 0, 0 that will give you a profit of 0. If you make no corn and no soybeans, you'll get $0. Right? I didn't put that in there. Anyway, here's what it looks like when you test the points. And you see we have all of them there, and we can see that we can make all different kinds of profits based on how many acres we assign to be corn and how many acres we assign to be soybeans. We can make all kinds of profits. So what would be the best profit? Looking very closely here, this one is the largest number I'm getting. It's telling me, based on all of this stuff that you told me, that you only have 6,000 acres of a farm, and you can only take $240 per acre in a profit of corn and so on, and all these other situations you have about labor and all that. I'm going to tell you, if you could choose to do 3,750 acres of corn and 2,250 acres of soybeans, then that will give you the best profit, which will be 1,260,000. That's the point of it. See a question. Let's see if we can answer. The question is, do we have to plug them all in to get the answer? The answer is yes. That's just what you do. And you have to do each and every single point because there is no rhyme or reason to which one it's going to be. Sometimes it's going to be the one you thought that it wouldn't be because it has a 0 in it. Like you just really do have to test each and every single one of them. Yes, you do. And that's what the work is that you see here on the bottom right is a test of each of the corner points. And in this case, we had to also make sure we make up an objective function. Sometimes they give you an objective function, but if you have to make it up, here you're trying to maximize profit. What if this was not profits, but instead it was costs? You'd be trying to minimize costs, so you'd have an upside down one and you'd get corners and you'd try them all, but you'd go for the lowest number because you want to pay the least in cost. All right. So yes, we're going to go ahead and graph these and then find those points and then take each of the coordinates of every point and plug them into the objective function to see what the objective function yields. And that's how we're going to determine and then we're going to make a decision and select the one that is the greatest and say the answer is 3,750 corn, 2,250 soybeans, and the profit would be 1,260,000. Okay, so that is the whole situation, my friends, when it comes to linear programming. And I know you guys are really enjoying yourselves here in quantitative analysis, but I kind of have just about one more to do, and we're just about done. I only have one little one, and then we're going to be done. I hope you don't mind that we're going to dismiss early today, because we are just about done. I'm going to stick around if you need to talk to me, though, and if you want, you could start your homework. I'll be here, but we're going to be done with our lecture probably in about 15 minutes. Here, example 3. Let's do a minimization case. Find the maximum and minimum values if they exist for a special function of c equals x plus y for these constraints. So this should not be really very challenging. All you got to do really is just use this as your objective function, go into Desmos and get all of these. And then when you're through, check each of the corner points that you find. Here's a hint, you should get something looking kind of like what you see right here, right? And then check them all and then see what you get. I'm going to give you 5 minutes. In 5 minutes, we'll come back and I'll reveal the answer. It's 5:21 and 5:25. I'll reveal the answer. Everybody, please focus with me and try this with me. Go through the motions of what I just explained. Go into Desmos and see if you can get the answer. All right, we'll be back in just 5 minutes. So as you can see, we have the solutions here. Basically, what you would do is you would go and put them into Desmos. You get an image kind of like what you see on the left. Then you would use the corner points that you found there and put them together with that cost function, and then see which of the answers you get for the corners. And then for the corners, as you can see, we had one at 0, 6, one at 11, 0, and one at 2, 3. So we just use that capital C and put them in and find out what we get for each case. And in each case, we have numbers. Notice that there is a minimum value of 5, but because of the picture, we should know there is no maximum value. And as you can imagine, with the blue dots, rather with the blue shading, there are points in that shade that are far, far up into infinity. So there is no maximum. The only way you'll ever know that is by looking at a graph. You can't see that anywhere in the algebra of it. You must look at a graph to be able to determine those situations where you have no max or no min. Okay. All right, guys, I think that's all I got for you. Let's take a look here, right? Isn't that the end of my lesson here? Let me get rid of those purple rectangles. I'm going to close our lesson here, and I'm going to post this video for you in your module 5A so that you can go and watch it whenever you want and rewind it and pause it. Maybe it'll help you if you can't remember something, you could come and back and remember our conversation today. I'll stop the recording and then I'll open up the floor to questions. So in closing, thank you so much for your attention, and everyone have a good night.